Hello students, it is the fourth lecture on vectors, and today we will discuss some vector applications, some properties. First of all, I already discussed with you unit vector. I want to give you a few more examples on unit vectors. Point number one, unit vector. You already know what is a unit vector. Unit vector whose magnitude is 1 and has got a direction of a given vector. So, if it is a unit vector, its magnitude is always 1. The application is, what is the unit vector for, suppose I have a vector 2i plus 3j, and my question is, what is its unit vector? Unit vector of this vector, two-dimensional vector, a planar vector which has two components. What is its unit vector? What is its direction? So that will be given just by definition. We know unit vector is vector by its magnitude. This is the definition for the unit vector. So in the present case, what is the unit vector for this 2i plus 3j? The answer is quite simple. Unit vector, this vector a here, but this vector is here, 2i plus 3j whole divided by magnitude a, and you have to write magnitude of this vector, that is root of 2 square plus 3 square. So it is n unit vector is equal to 2i plus 3j divided by root of 9 plus 4, that is 13. This is the unit vector for this vector. Means this vector has this direction. And if I ask you what is the magnitude of this unit vector, that is 1. You can find it from the right side that it is magnitude is 1. And if I give you some another example, suppose we have a vector, S vector is equal to, okay, minus 2i plus 4j minus 2k, suppose. This is a vector. And my question to you students is, what is its direction? So for that you have to find its unit vector. So you just write n unit vector is vector S by its magnitude. So what you are going to do now? You are going to do now, you have to write the vector as such here. तो नीचे से जो s है, that is simply the magnitude of this vector s. So you write n unit vector is equal to minus 2i plus 4j minus 2k whole divided by s. Now what is s magnitude? That is, as usual, 2 square plus 4 square plus 2 square again. So if you simplify this, that is minus 2i plus 4j minus 2k whole divided by 4 plus 16. 4 plus 4 plus 16. 4 plus 4, 8. 8 plus 16 is 24. 24. Okay, this is the unit vector for this given vector. So if I ask you what is the direction of this vector, this vector has the direction of this vector, this unit vector, and the magnitude of this unit vector is just 1. Okay, it was, I have already talked about unit vector. So there I wanted to give you some examples of how to find unit vectors of some vectors. So this is the technique, just a vector by its magnitude, write the full vector, divide by its own magnitude, you will get a unit vector. Okay, now second point is how to add 2 vectors or even 3 vectors, how to subtract vectors through components. That becomes very easy and handy. One method is, as you know, if you want to add 2 vectors, that you have the rule root of magnitude of one vector square a square plus b square plus 2ab cos theta. That is the simple rule how to add 2 vectors. And how you subtract 2 vectors, you have again the rule a square plus b square minus 2ab cos the root of that. So it is the way how we add 2 vectors or how we subtract 2 vectors. On that I have already a lecture which is already uploaded on the YouTube. You can watch that. But there's one more technique, handy technique, and a very simple one and mathematically more consistent. That is how to add too many vectors, how to subtract vectors through components. It becomes quite easy and mathematically quite consistent. So let me go to that. Point number second. Point number second. Okay. Now, suppose I have a vector A is equal to 2A plus 4J. It is a planar vector. If I ask you in which plane this vector lies, the answer should be XY plane. I means X, J means Y, XY plane. If I ask you what's the magnitude of this vector, you can write 2 square plus 4 square root of that. And you can also find the direction that we have already discussed. And that we have already discussed. So there's a vector B, let me suppose, vector B, that is, okay, that's I plus 3J. I plus 3J. Now, what is A plus B vector? It can be done like this. So that is what I say when I explain that how to add two vectors through components. It becomes quite handy, straightforward and elegant, mathematically elegant in some ways. So पहले आप ये लिखिए. It is A here, write down the A vector in vector form, in component form, plus B. For B you write I plus 3J. Right? Now A plus B, okay, vector C, let me suppose it is 2I plus I means 3I. 4J plus 3J means 7J. This is the answer. Quite simple. Now if I ask you what is the magnitude of the resultant of these two, A and B, simple, root of 3 square plus 7 square. If I ask you what is the direction, means what is the angle this vector C makes with x-axis or even with y-axis, you can find that theta is tan inverse, that is 7 by 3. But this is the angle this vector C makes with the x-axis. If I ask you what is the angle it makes with the y-axis, then it will be 3 by 7. Iska ulta karna hai. Okay. Now, how to add three vectors? Same technique. Suppose A is 2I, the vector B is 4J, vector C is 2I plus 3J minus K. And my question is, what is A plus B? Okay. Let me make it minus C. How to find this? Very simple. Substitute for A, B and C from the given equations and then try to find out and go through some mathematical steps and finally get the answer. So how it is that? 2I here for A, and for B it is 4J, and for C it is 2I plus 3J minus K. So simple. For A this, for B this, for C this. There's no. For C I have to write negative sign here and this I have to put in the brackets because negative is to be multiplied to every part there inside the brackets. Here minus here, but in the brackets there is whole C. And here you have to go through some mathematical steps. It is 2I, it is plus 4J minus 2I minus 3J plus K. Okay, now this whole vector is some kind of a resultant vector or is equal to, it is 2I and 2I, they cancel because one is positive, other is negative. You do it just the way you are doing simple algebra. उसी हिसाब से कीजिए आप, उसमें कोई प्रॉब्लम नहीं है. 4J और 3J को, इस 3J को सब्ट्रैक्ट करना पड़ेगा तो आपको J लिखना पड़ेगा प्लस दैट K. That is the answer. That is the answer. So what is the magnitude of R? It is J का जो कोफिशिएंट है that is 1 square, जो K का कोफिशिएंट है that is again 1 square, that is root 2. And you can also find direction. Theta is equal to tan inverse what? Okay, 1 by 1, that is tan inverse 1, and it is 45 degrees. That's all. So this I wanted to tell you how to deal with this is a kind of vector algebra. When you go ahead with your syllabus to different fields of physics, maybe electrostatics, magnetic field, electrostatics, current, electricity, and there is even optics. Everywhere you need to use some kind of vector algebra, and this is what we call as vector algebra. How you apply vector rules to equations. And point number 3, third point. Point number 3, very important point. Third point is dot product of two vectors. Dot product, also called as scalar product. Product of two vectors. ये तो कैसे आप इसको डील करेंगे? First of all, let me give you the definition. Dot product of two vectors is defined as the product of magnitudes of two vectors, and cos of angle between the two vectors. Something like this. Written as A dot B. This is read as A dot B, but defined as magnitude A, magnitude B, and cos of angle between them. That is all. It's a definition. We have to always remember the definitions. So again, I must tell you, the dot product of two vectors is a product of magnitude of A, magnitude of B, and cosine of angle between those two vectors. Okay. By this definition, what is, if theta is 0, what should be A dot B? A dot B should be AB. Simply because cos 0 is 1. Achha, okay. If agar theta 90 hai to, then A dot B is what? AB cos of 90. Okay. So what is AB in that case? In that case, A dot B is equal to 0 because cos 90 is 0. So here you can put it in other words. If the dot product of two vectors is 0, then they are perpendicular to each other. Or if the dot product of two vectors is 0, then they are perpendicular to each other. Or other way around also. If you have dot product of two vectors as 0, you can well understand that the two vectors should be perpendicular to each other. Okay. If theta is 180 degrees, then A dot B is what? Then A dot B is minus AB. Why? Because cos 180 is minus 1. So these three things you need to remember. But here one important thing is that if the dot product of two vectors is 0, then the two vectors have to be normal to each other. Okay, this is one part. Second part is, if I want to put this A into components, B also into components, three-dimensional vector components, then what should be the dot product? So let me put A and B both in terms of components. So what I am going to get in that case? Okay, before I do that, I must tell you by this definition that we have framed for the dot product, what is I dot I? A dot B is AB cos theta. So what is I dot I? That is magnitude I cos of 0. Because what is the angle between I and I? Because these are the two unit vectors in the same direction. 0. It is 1. It is also 1. It is also 1. 1. What is J dot J? Same as 1 by the same argument. What is K dot K? That is also 1. So if I dot two unit vectors, the dot product of two unit vectors is always 1. Same unit vectors. So if I do it like this, what is I dot J? What should be I dot J? The I dot J, they are perpendicular to each other because I has this direction, J has this direction, and K has this direction. They are mutually perpendicular. this is perpendicular to this, and this is perpendicular to both this and this. So it is something like this. This and this. This is x, this is y, this is z. They are mutually perpendicular to each other. They make 90 with each other. So what is I dot j? That's magnitude I, magnitude j, cos of 90. Because of the angle between I and j, that is 90, is 0. That's k dot j. J dot k is again 0 and k dot I is again 0. So here you have to remember dot product of similar unit vectors, same unit vectors is 1, and dot product of two unit vectors which are perpendicular to each other, normal to each other, their dot product is 0. Okay. Now with this definition or with these additional information that we have now, let me again find A dot B. Let me see what this A dot B is equal to. Let me see. Okay. Okay. Now, fourth point. Let me call it now fourth point, or it is under the same heading because it is the same concept going on. So long it is same concept going on, we will not change the number. So what is A dot B again? Write A in terms of components. It's a space, let it be a space vector as a general case. It can be a planar vector. It can be a vector in a single direction on the x-axis. But in general, let me say it is a space vector and it can be put into three components: axi plus ayj plus azk. Dot with what? B. So what is the space components of vector B? Write it down here. That is bxi plus byj plus bzk. These are the two vectors, components of A dot here and components of B. So now let me go ahead doing some mathematical steps, a few, maybe 1 or 2 steps, and I will get an equation which will tell you physically something. It is the end result which is important. Sometimes the derivation, a few steps that you go through becomes important, and sometimes you have the occasion to learn certain things during the derivation. And in most of the cases, the end result gives you the physics. The end result becomes important. And for NEET students or IIT students, it is always the end result which is important. That becomes a rule, that becomes a formula which you need to apply in real-time situations, in real-time problems, in physics. Okay, now this A dot B is AXI, I will dot it BXI. I dot I is 1, so it becomes AXBX. Component of X component of A and X component of B plus. Now I will dot this I with this, that will become 0. I will dot this with this, that will become again 0. I will dot now this with this, it will become a 0. J dot I will become 0. Now I will dot this with this, that will become AYBY. Then this will become 0 with this. Now this will become 0 with this will become 0 with this will become something with this, that is AZBZ. It is because I dot I is 1, J dot J is 1, K dot K is 1, and other crosses, other dots are 0. Means I dot J, J dot K, K dot I are all 0. That only this survives. This becomes the formula. What does the formula indicate? The formula indicates that there is no I, J or K on the right side. Obviously, there is no I, J or K on the right side. Does not appear on the right side of the dot product. उसका मतलब क्या हुआ? उसका मतलब ये है कि dot product is a scalar quantity. Dot product is scalar. Is scalar. Dot product is scalar. Okay. Now let me give you a few examples of this, how to find dot when vectors are given very quickly if we are able to do this. Let me do a few examples, not more, a few. a few examples. Fourth, let me go to the point number 4. Although the same concept goes on, fourth point is, have a look. Suppose I have a vector f that is 2i plus 3j minus k, and s is equal to I plus 2k plus 2j plus 3k. What is f dot s? As per the definition and the formula, it is fx sx plus fy sy plus fz sz. This one, and this one. So what you would do with this? Fx is what? 2, fy is 3, fz is minus 1, k ka coefficient. Now what was s? Sx is 1, I का कोफिशिएंट, sy is 2, j का कोफिशिएंट जो है, sz is 3 जो k का कोफिशिएंट है, s z 3. Now f dot s is equal to fx sx. Fx is 2, sx is 1 here, right? Multiply them. It is 2 into 1 plus fy sy. Multiply these two. 3 into 2 plus fz, that is 1 minus 1, and sz plus 3, that is minus 1 plus 3. That is f dot s is 2 plus 6 minus 3. That is 5 is the answer. This is how we do the things. Multiply these coefficients, multiply these, but this is negative, this is positive, and finally this minus into plus will become minus here. This will become minus. Okay, this what are the applications of this dot product? Dot product is used where you see when we go to the work, power and energy. Work done is a dot product of force and displacement. It is not force multiplied by displacement, that is the dot there. And then again power, mechanical power is F dot V. So in many cases in physics we have to use this dot product. So you remember it from here how to analyze the dot product of two vectors. Okay, now let me go to one important fact about this dot product. So that important fact is this dot product is a scalar, and as such this scalar does not change if you rotate the coordinate system. What do you mean by that? Okay, let me explain. That's a very important point. Dot product remains invariant under the rotation of coordinate system. Let me explain that. That's very important. I will make a coordinate system first. Let me make a coordinate system. Fifth point. Have a look. First of all, let me write, and you remember the statement before I explain this. Dot product is scalar and remains invariant under the rotation of coordinate system. Under the rotation of coordinate system. वैसे भी all the scalars remain invariant under the rotation of coordinate system. So dot product is no exception. But I will prove this how dot product remains invariant under the rotation of coordinate system. Have a look. This is a coordinate system x and y, and you have this vector A. You have vector A. Okay. Now, what is vector A dot A? What is vector A dot A? That's magnitude A. That's magnitude A into magnitude A cos of 0. Angle between A and A, that is 0, because both are the same vectors. They have the same direction. The angle between them should be 0. So it is A square. So A dot A, vector A dot vector A is A square. Any vector dot with the same is the square of that. B dot B is B square. Okay, F dot F is F square. No exceptions. ठीक? I have proved it here. It is What is good here is good everywhere. What's correct here is correct everywhere. Okay. Now, what is the component of this vector on this x-axis, ax? Okay. What is component here? Ay. Component here is ax, component here is ay. Can you write what is a square, magnitude of square? That is ax square plus ay square, that is a dot a. Again, I will explain this. This vector is put into two components, this and this, and I will write a square, that is a, dot product of two vectors. Maybe it is the dot product of same two vectors or a different two vectors, same thing, ax square plus ay square. Okay, now let me rotate the coordinate system. Let me rotate the coordinate system. What will happen? What is going to happen if I rotate the coordinate system? What is going to happen if I rotate the coordinate system? I will rotate the coordinate system. Have a look. I will rotate the coordinate system. This x-axis becomes this x prime and this y becomes y prime. Now I will find the components of this vector on x prime and y prime. Draw a perpendicular on the x prime. So from here to here it is ax prime. And now I will draw a perpendicular on this y prime, that is this. From here to here it is ay prime. Again tell me what is this a vector in terms of new primes, ax prime and ay. It's the same vector here. Have a look. It's the same vector. Now it has this component and this component. So again this vector a square is equal to ax prime square plus ay prime square. It is again a dot a. So in the new prime system, it has the same magnitude. So that means magnitude square or a dot a remains invariant under the rotation of coordinate system. Of course, ax is not equal to ax prime. The components have changed when you rotate a coordinate system. Ay is not equal to ay prime. No, they are not equal, as you can see. If you rotate a coordinate system, these components, individual components are not the same. Ax prime is not ax. Yeah, ay prime is not ay, is here, ay. They are not equal. So at least one thing is clear now. If you rotate a coordinate system, the components of a vector change, right? Or even ax prime square is not equal to ax prime square. No, they are not equal. If they are not equal, how come their squares be equal? So ay square is not equal to ay prime square. But as a matter of coincidence, what is equal? Ax square plus ay square, this one, is equal to this one. Ax square plus ay square, sum of the squares of the components is equal in one coordinate system, original coordinate system, is equal to sum of the squares of the components in the rotated coordinate system. Again I will explain. Sum of the squares of the components in the xy coordinate system is equal to sum of the squares of the components in the x prime y prime coordinate system which you have rotated. These are equal. Not this, not this, not this, not this, but sum of the squares are equal. That means a dot a is invariant under the rotation of coordinate system. Under the rotation of coordinate system. That is all. This is all for today. In the next lecture, I will explain cross product, and then certainly I will solve problem sets with the students so that vectors become quite clear. Okay, thank you.